Hello and welcome to Engineering Economics, Lecture 2-1, and we're going to talk about interest. We're going to get started with money. Good old money, money, money. So, first thing, let's do a quick return to our principles of engineering economics. Remember that a nearby dollar is worth more than a distance dollar. And when we talk about distance, we talk about distance in time. So we're going to get into the concept of time value of money. And you really should know all about time value of money, because money now and money in the future and money in the past have different values. The other principles of engineering economics, when you're considering alternatives, the only thing you worry about are the differences in those alternatives. Marginal revenues must exceed marginal cost. That's kind of a no-brainer. And you don't take on more risk unless you get more return. So, first, let's talk about the concept of an interest rate. And an interest rate, or interest, and interest rates and interest are different things, by the way, are a manifestation of the concept of time value of money. So you can look at interest as the amount that you pay in money to use money. Okay, when we say use money, it could be borrow money, lend money. Interest applies to both of those. So you have the concept of investments and the concepts of loans. Pretty straightforward. Investments, you put money in and you want to get more money back. A loan, you borrow money and you're going to pay back more money. Okay, it's essentially a fee. And when we talk about the rates, we typically talk about them as a percentage. Okay, and we all think everybody should understand the concept of percentages, but we talk about rates, interest rates, and return rates in terms of percentages. But one important point here is interest is the amount of money you either put forth or get back, and the rates are the same thing in percentage. And that percentage is important because it has to do with the original amount of money that you invested or the amount of money that you borrowed. Simple example. Easy. You borrow $10,000, 7% interest. Okay, guess what? You're going to have to pay for that money. If it's 7% interest and it's 1 year, it's going to be $700. Pretty straightforward. Okay, N of 1. Okay, the amount is the difference between the amount of money that you paid back, the amount of money that you originally borrowed, and there's your interest amount with $700. And the interest rate is just the 700 divided by 10,000. That's pretty straightforward. I think most of anybody can do this calculation. I think it's kind of like one of those ones you should have done in grade school or high school. Know your money. Notations are important here because we're engineers and we typically try to use the same variable names for this as we go along. So I, that's the amount. Dollars, euros, rand, whatever. Little I is the rate. Percent. Okay, it actually is percent per interest periods, and interest periods can change. We're talking, right now we're talking about annual, percentage, annual interest, but we're going to talk about different interest periods in the future. N being the number of interest periods. This last problem was 1 year, so your interest period was 1 year, and it was easy. But N doesn't have to be 1 year. And how much did you borrow? And again, we're going to also look at this as borrowing and investment. Again, pretty straightforward stuff. Shouldn't have any trouble with that. But just remember, big I, little I, and P. Now, let's see. If you borrow $20,000 for 1 year at 9% interest, okay, how much should it cost you? Well, pretty straightforward. 9%, 20,000, okay, $1,800. Okay, you're going to pay back $21,800. Now, we're going to be doing a lot of calculations with this. I would highly recommend that if you do not know how to use Excel, that you learn. And if necessary, I will create a series of lectures of how to do some of this stuff in Excel. The reason for this is straightforward. You can do this on a calculator. Most of you can probably do this in your head. But it's going to get much more complex. And the more complex than that, we're going to have a lot more numbers. Stuff is this part, so far, it's not real hard. In the investment side, same concept, okay? If somebody borrowed $20,000 from you and 9% interest per year, or maybe you invested it in something and it had 9% return. How much money did you get off of that? $1,800. Well, yeah, that was your rate of return, but it isn't that simple. That would be how much your rate of return would be if money didn't change value over time and you didn't have to pay any taxes on it. Guess what? Those other two things are going to definitely apply. So let's talk about that. Money does change value over time. So even though you made 9% on that and you got $1,800 and you got $21,800 a year from now on the $20,000 that you originally lent, reality is that if inflation was 15%, you ended up losing money on it. So guess what? You are, in big terms, going to have to adjust what you actually made for inflation. So inflation, guess what? It reduces your purchasing power, it increases your operating costs, and it reduces your rate of return on investments. That's why we don't like inflation that much. But there is rates of inflation that are reasonable. For the most part, we really just like it to be stable and predictable. That's what people that borrow, lend money, and that's what they would like to see. Guess what? Taxes. Yes, many of the different things that you might, when you're lending money or borrowing money, taxes play a role. Again, if you were to lend money and you had to pay taxes on the amount that you made off that money, you now have an after-tax cash. Okay, so effectively, you didn't get 9%. You probably got less than that because you had to pay some taxes on it. So we have after-tax cash flow and before-tax cash flow. And smart enough to say, hey, I need to take these two factors into account. Another thing that we're going to look at here is a simple cash flow diagram. And the cash flow diagram is pretty straightforward. It's just a line with, okay, if you got inflows, okay, arrow pointing up. And if you got outflows, arrow pointing down. Okay, disbursements, receipts, revenues. Okay, it's again, pretty straightforward. And the simple cash flow diagram only has one period in it, 1 year period, and it's annualized, so you're only going to show one up, one down. But reality is that they're pretty useful in that you can actually show multiple years, and you'll see that we're going to have some examples of cash flow diagrams as we go along showing multiple years, because right now we've just only dealt with 1 year in an annual interest rate. Again, it does get more complex, but right now, pretty simple stuff. If you've got a rate of return or you've got an interest rate and you've got an initial amount and you got a final amount, present amount, future amount, it's boom. You just calculate by multiplying by the percent and then adding it to your original or subtracting from your original, which way you go. Now, interest. Interest is not so simple, but we do have simple interest. In the concept of simple interest, you basically charge the interest rate only to the initial sum of the money, regardless of the number of pay periods that you have, or what we call N, okay, number of interest periods. Compound interest, and by the way, simple interest, again, not something you see a lot. Compound interest is what you do. And that's when you say, okay, look, we're going to charge the interest rate to the initial sum, but then the initial sum is going to change in the second year. And then you have to charge the interest rate to that new sum. So simple interest is that easy. Okay, if you had a beginning balance of 1,000, year one, $80 if it's 8% interest. Year two, $80 if it's 8% interest. Year three, $80 if it's 8% interest, because you're only multiplying the 8% by that initial 1,000. So simply you can just add, and whoop, you got your final number, which is just 80 times 1, 80 times 1, 80 times 1 for each individual year. So 80 times 1,000, and you add those up. Okay, again, I think everybody should be able to calculate that one. But guess what? You don't use that very often. You're going to use the concept of compound interest. So the simple interest rate formula is really just you start with a certain amount, you multiply times the number of periods in the interest rate, and you add them all together. And voila, it's pretty easy to do. Now, what's important there, I think common sense kind of tells you how to do this, how this formula works. But When you get to compound interest, it definitely gets a little bit more complex. And it actually is going to get more complex as we talk about other ways of actually doing calculations in the future. But let's first start with the next simple one, compound interest. Okay, so in this case, you charge the interest rate to the initial sum in the first period. But now you have a new number of amount of money that you have or you have borrowed. Okay, guess what? You got to take it for the next period. You got to multiply by the new number. Easier to see in a calculation. So you got a beginning balance of 1,000 of 1,000. Okay, and 8% interest. Well, that's going to earn 80. So now you got 1,080. Period 1 is over. Now we're in period 2. You got 1,080. We're going to throw that 8% times that 1,080, which is now 8640. So you got more money in interest earned in the second year because, well, you had more money in the second year. And now your total ending balance actually goes up by a little bit more, 1,166.40. And then in year 3, you start with a bigger number. You multiply the 8% times the bigger number, and you even get more interest. Boom. So interest is nice because interest can compound up. You go up at a higher rate. Okay? That's a good thing. But that's also very much how it is done. So you want to show that on a diagram. It's pretty straightforward, but you can see that, the year 1, you got 1,000, you multiply by 8%, then you've got 1,080 in year 2, and then you multiply 8%, then you got 1,166.40 in year 3, and you again multiply by 8%, and it just compounds as you work your way through. If you got questions with this, I'd start hitting the discussion boards, but I think right now everybody should be okay with these concepts. Because now we go a little bit further. So the compound interest rate formula, you don't have to do it period by period by period by period by period and add all the periods because it pretty much is a very straightforward, when you look at the series, it's just that it's the principal. Now you take the 1 plus the interest rate to the nth power, where n, the big N, is the number of periods, and that tells you what it's going to be. So if I went backwards through the slides and I just applied 1 plus 0.07 to the third power, you'd find that you would have gotten the same answer. Now remember, if it's 7%, it's not 1 plus 7. 7% is actually 0.07. Okay, common mistake. I know it sounds crazy, but you're not taking 8 to the nth power. 1 plus 7, you're doing 1 plus, this is, I think it was 8% interest. Okay, whatever the interest rate was, 1.08 to the nth power. Well, again, it's 1.08, not 9 to the nth power, okay? Percent is actually times 100. So, boom, same answer. Yoo-hoo. That's kind of what we expected to see. Now, this is important. The concept of equivalence. Now, in the case of this example, which is actually meaningless in the sense of money, if you got different sets of units, different numbers can be equivalent. 68 can be equivalent to 110. Just because you're talking about the difference between miles per hour and kilometers per hour. Okay, the numbers aren't equivalent, but the actual speeds are equivalent. Now, when you're talking about this with money, that's called economic equivalence. Okay, now, a piece of money, a chunk of money right here, and a chunk of money at a different point in time can be equivalent, but the numbers won't be the same because interest rates and time periods separate those two values. Now, when we talk about economic equivalence, what I mean by important is that when you compare money, when you compare investments, you've got to look at, are they equivalent at the same point in time? So you need to calculate the economically equivalent value, and that equivalent value is based upon an interest rate and a time. Because distance money is not the same as near money. And when we talk about distance and nears, we're talking about time. So, remember that first question, that first problem that we saw. We had $20,000 and we had in the future, 1 year down the line, it was $21,800 paid back on the initial amount borrowed. Okay, so at 9% interest with per year and a 1 year difference, 20,000 is equivalent to 21,800. But the reality of this is that 20,000 isn't really said to be 20,000. It's 20,000 at time 0. And the 21,000 can be actually called 20,000 at T1 at 9%, or 21,800. You can actually say that it's 20,000, comma 1, comma 9. Okay, and it is the equivalent. It's equivalent. So those are the same thing. Okay, magnitude is not the same, but they're the same thing because they're not at the same point in time with that specific interest rate. So it's the timing, it's the interest rate, number of interest periods. That's how equivalences work. Got it? Timing, interest rate, number of interest periods. Now, right now we've been dealing with really simple things where you've got like, okay, here's a chunk of cash and here's that chunk of cash in the future. And just looking at an investment or borrowing. Okay, it's going to get a little bit more complex because maybe we got a chunk of cash and then we use a little bit of it here, and then a little bit later we use a little bit more, and then a little bit later we use a little bit more. Got to take those things into account. But right now, we can look at this in a lot of different ways. The formula is the same every single time in these. Okay, 8% interest was the equivalent worth of $2,042 now, 5 years from now. This isn't really that hard because the calculation is just simply that principal, 1 plus interest rate to the number of periods. So that was pretty straightforward, 3,000. Okay, and you can work backwards. What about 3,000 in the future? What is it worth right now at this interest rate if we're looking at 5 years in the past? Okay, so easy, relatively straightforward to do. That one equation. Okay, P, 1 plus I to the n. Poof, done, easy, quick. Going to use it over and over again. At what interest rate would these two amounts be equivalent in 5 years period of time? Well, it's not that hard because really all you're doing is solving for, in this case, we're solving for I, or we're solving for the interest rate itself. So you just do that. You solve for I. And in this case, we're just showing you an example of I at 6, I at 8, I at 10. I at 10 gives you 3,289. It's a little bit more, it's a little bit harder to solve for the I inside of the 1 plus I when you're actually doing it algebraically. But the concept is you're just solving for one of the variables. Okay, so an interest rate of 10% makes those two values equivalent when they're separated by 5 years' time. Same exact thing here once again, going backwards. Okay, if something's worth $5,877.32 in the future and you got an interest rate of 8%, how much is it right at this moment in time? Same equation. Okay, remember it was, in the case here, it was F equals P times 1 plus I to the n, but okay, all we're doing is we're solving for P. Okay, F over 1 plus I to the n, or you can say F times 1 plus I to the negative n is another way to actually state that. And again, same equation over and over and over again. Remember that equation, memorize that equation, know that equation. You need to know that equation. It's used all the time. It's just a simple, straightforward mathematical equation to do compound interest, and it's something that's done all the time, everywhere. So, the concept. How many years would it take an investment to double at 10% annual interest? Well, if you can get 10% annual interest, go for it. Now, I've had some investments that are better than 10, but 10 is a good one. How long does it take for it to double? Well, okay, this one's pretty straightforward because all you're going to do is say that the future value is going to be 2 times the present value. So when you divide future value, or you divide future value by present value, you got the number 2, and you solve for n, and you get 7.27. Same equation, okay? Again, not doing anything super fancy here, which kind of leads you to this concept of the rule of 72, which is a quick and dirty way to approximate how long it takes for a sum of money to double. You just take 72 divided by the interest rate, and if you put 10 in there, it does that. Again, the farther you get away from 10%, you know, the farther off you're going to be. But if you had to really, like, you know, quick and dirty, do, okay, how long is it going to take me to double my money? Okay, you're going to just do that interest rate. Okay, if say said 5%, you're going to say, oh, it's roughly 15 years. Okay, well, you'd say 7.2, 14 years, 14.4, but I'm going to go 15. Play conservative. So let's look at some formulas for cash flows. And this has got some terminology that you need to learn. So, single payment compound amount factor or growth factor. Okay, here, and note, the annotation here is important. F, okay, we already know that F is equal to P of 1 plus I to the N, but what we're really looking at here is the annotation of F over P, I, and N. Okay, it's a factor, growth factor. Okay, now, simple problem, look at that. If you had $2,000 now, you invested at 10%, how much would it be worth in 8 years? Okay, well, you can do this calculation. You've got everything that you need. You know all the equations. And if you did this, you'd say, okay, P, 2,000, I, 10, and 8. Find future value, $4,287. Okay, you can do it with, and I'll show you the Excel command here because there is an FV command in Excel that does this. It's going to give you the same answer. Nice to know, okay? In 8 years' time, $2,000 invested at 10% interest, it's going to be more than doubled. Woohoo! Okay, not too bad if you can get 10% interest. So the single cash flow formula is simply that formula that you've looked at. Now, I have 12% interest, okay, little I, in 5 years, F of 1,000. Okay, now notice when I said the formula is, okay, is the future divided by 1 plus the interest rate to the n, or anybody know a little bit of algebra, just to the -5, or you notice the annotation that we've got right there, P over F, 12%, 5%. Throw in the numbers, and you find that the present value is 560. And I always going to call it present value. The current principal or the present value is 567.40. So if you look at the numbers now, they should start kind of. I'm hoping that they're making a little bit of sense to you. 12% interest is a little bit more than 10. 5 years, you're looking at $1,000. Okay, you're saying, well, you knew that at 10% and 7.2 years would actually see a doubling. So now with these different interest rates, the interest rate being a little bit higher, the 5-year period, it's not quite a doubling of the 567.40, but again, interest rate's higher, but the period was less. I'm hoping this is actually kind of, making a little bit of sense. Remember, how long does it take to double your money at 10%? And that's a number to remember, 7.2 years. Why do you remember that? Because it lets you reference whether things are going to happen faster or slower for doubling. Now, another problem, you want to set aside a lump sum today. This is the thing that you do. Okay, I need some money to go to college 10 years from now. My children will be going to college. That's a future value. I'm going to put that money aside right now. Okay, you know how long it's going to be? How much you need to put in right now? Now, more than likely, you're not going to put it all in as a lump sum, but hey, let's just pretend. Again, back to the same equation, and you can easily calculate, remember, P equals F, 1 plus I to the N, boom, 6,663. Now, what if we've got multiple payments, withdrawals, Okay, how do you do that? Okay, before I move forward, I want you to think about how would you do this? Now, go back to like the 7th slide I gave you. Equivalence. Everything can be brought to a single point in time. They all have an equivalent value at this, if you can bring, so I can make that equivalent value anywhere along this timeline, but really what I want to do is I want to solve for what it is today. So what do I have to do? Equivalence. Well, each of those individual pieces can be made equivalent. So we do that. Payment series isn't even, but we can calculate the present value or the principal needed for each of those. Once you have the principal needed for each of those withdrawals, you simply add them together. Concept of equivalence. If you did this correctly, you got it right. Okay, equivalence. Now, this shows it on a timeline, but again, don't overcomplicate it. Each of those individual withdrawals brought back to the equivalent value at the beginning point in time, added together tells you how much you need to put in at that point in time. These are likely going to be a little bit more complex because you're probably not going to put it all in at the first point in time. You're going to probably put it in at different points in time. You take some out here, put some in there. That's why I say, spreadsheets, because now you got a bunch of calculations that you've got to do. And you can say, at this point in time, I put this in. At this point in time, I took that out. You can still put them all into a level of equivalence. And if you check this, okay, the equation is the same each time. And if you look at the very end, you should have an ending balance of 0. You put this up front. You took this out. You took this out. You took this out. And you should be at 0. In this case, we end up at 47 cents. But that's because we rounded off. Now, the P, we've called it the principal. We've called it the present worth. We've called it the present value. We can call it the net present value. We can call it, okay, there's multiple names for it depending upon how you're using the money and what kind of calculation you're doing. But essentially, the P is the value of the money at time zilch, 0, at the beginning, the start. Okay, so that's at the fixed point in time we call 0. F is at that fixed point in time that is after 0, somewhere in the future. Okay, we can also call it future worth or future value. That's pretty straightforward. A. Now, we aren't doing a lot of stuff with A yet, but we will. Series of consecutive equal end of period amounts of money. Now, this may be amount of money that you put in. This may be amount of money that you take out. We call it annual worth, equivalent uniform annual worth. Okay, and N is important because it's the number of interest periods in the concept of using an annual interest rate. The N is in years, annual, years. But it doesn't have to be in years. It can be in months. It can be in days. There's another case that you're going to consider where it can be continuous. Okay, that's a little bit more complex, but again, it just adds something to the equation. The concept, however, is no different. So I, interest rate, rate of return for that specific time period. And T is the time, okay, and the time given in the number of periods. So if you're talking about a daily interest rate, the time is given in days. If you're talking about a monthly, again, not, considered to be terribly, terribly hard. All right, that is the basics right there. That one equation, and yes, I do expect you to memorize at least that one equation. The other ones you might want to write down because we're going to be talking about all sorts of other ways of dealing with money and money over periods and monies in annual, and basically different ways we play with money. I'm not even going to start into it because you're going to get a bunch more lectures that go into this Have fun. This, however, is the basics of what you should know, not so much as an engineer in the engineering economic sense, but as a person who does have and will make money and invest money and withdraw money and borrow money, the basics. Know this. So hopefully you enjoyed this little lecture here, and we've got more to come.